Welcome! In this session, we will explore an intriguing problem from LeetCode, titled Find kth bit in nth binary string. We'll break down the problem, analyze the approaches, and understand the solution step by step. Let's dive in. In this problem, we are tasked with finding the kth bit in the nth binary string. To generate the binary string s_n, we start with s_1, which is simply 0. For any value of n greater than 1, the string s_n is constructed by taking the previous string, s_n1, appending 1, and then concatenating the inverted and reversed version of s_n1. Here, the plus symbol represents string concatenation, reverse x reverses the order of characters in the string x, and invert x flips every bit in x, changing 0 to 1 and 1 to 0. Your goal is to determine the kth bit, or k is 1 indexed, in the resulting binary string s_n using these rules. The output of the problem is a single character, either 0 or 1, which represents the kth bit of the binary string s_n. Let's look at an example. If n is 3 and k is 1, the output is 0. Here's why: s_1 is 0. From s_1, we construct s_2 as 011 by following the generation rules described earlier. Then, s_3 is formed as 0111001 by applying the same process to s_2. When we look at the first bit of s_3, it's 0, so that's the answer. Now, let's consider another example. If n is 4 and k is 11, the output is 1. Breaking this down, s_1 is 0, s_2 becomes 011, s_3 is 0111001, and s_4 is constructed as 011100110110001. If we examine the 11th bit of s_4, we can see that it's 1, which gives us our answer. This demonstrates how the strings grow in length and how each bit can be identified based on its position in the sequence. Here's a simpler example to reinforce the concept. If n is 2 and k is 3, the output is 1. In this case, s_1 is 0, and s_2 is 011. The third bit of s_2 is 1, which is the result. These examples help to illustrate the pattern and symmetry in the binary string construction, which becomes critical as the strings get larger. The constraints of the problem are important to note. The value of n ranges from 1 to 20, which ensures that we cannot explicitly generate the strings for large n, as their lengths grow exponentially. For instance, the length of s_n is 2 to the power of n1. When n is 20, the string length exceeds 1 million, so a direct construction is computationally infeasible. The value of k is always within the range of the string's length, ensuring it's a valid index. Edge cases include small values of n and k, such as n equal to 1, where the string is minimal, and large values like n equal to 20 with k near the extremes of the string. Additionally, k values near the middle of s_n are interesting because they test the symmetry of the string construction process. To start, let's discuss the brute force approach to solving this problem. The idea is to generate the binary string s_n step by step using the recursive formula provided in the problem. We begin with s_1, which is simply 0. For each subsequent string s_i, we construct it by taking s_i1, appending a 1, and then adding the inverted and reversed version of s_i1. Once we've generated s_n, we can directly access the kth bit by indexing into this constructed string. While the steps are straightforward, the complexity of this approach is significant. The time and space requirements are both exponential, specifically 2 to the power of n, because the length of s_n doubles with each step. This makes the brute force method impractical for larger values of n. Now, let's consider an optimized recursive approach that eliminates the need to construct the full string s_n. This method is based on analyzing the structural properties of s_n. The key insight is that s_n can be divided into 3 parts: the first half, which is identical to s_n1, the middle element, which is always 1, and the second half, which is the reverse and inverted version of s_n1. By leveraging this symmetry, we can determine the kth bit without explicitly building the string. If k matches the middle index, the result is 1. If k is in the first half, it corresponds directly to the kth bit of s underscore n1. If k is in the second half, we map it to the appropriate index in s underscore n1, invert the bit, and return the result. This approach allows us to recursively narrow down the problem with minimal computation. The optimized recursive approach has a much better computational complexity. In terms of time, it operates in O(n), as we perform a constant amount of work at each level of recursion. The space complexity is also O(n), which accounts for the recursive stack depth. This makes the method far more efficient than the brute force approach, especially for larger values of n. One of the key advantages of this approach is that it avoids storing large strings, which is crucial for handling high constraints. By leveraging the structural properties of s underscore n and working directly with indices, we achieve a scalable solution. This strategy is particularly well suited for competitive programming, where both time and space efficiency are critical. The recursive nature of the solution, combined with the symmetry of s underscore n, provides an elegant and effective way to solve the problem. The brute force approach, although intuitive, falls short for larger values of n, especially beyond n equals 20, because the length of s underscore n grows exponentially. This makes the method infeasible within typical constraint limits. On the other hand, the optimized recursive approach, while requiring careful attention to detail and implementation, is far more efficient. It avoids the exponential growth of both time and space and relies on the structural insights of s underscore n to solve the problem efficiently. The trade-off is that it requires a deeper understanding of the recursive structure and careful handling of indices to ensure correctness. Ultimately, this approach is the clear choice, as it balances efficiency with scalability, making it suitable for tackling real-world problem constraints. To solve this problem, we begin by understanding the recursive definition of the binary strings s underscore n. The sequence starts with s underscore 1, which is simply 0. For any n greater than 1, s underscore n is constructed by concatenating three parts: first, the binary string from the previous step, s underscore n1, second, the character 1, and third, the inverted and reversed version of s underscore n1. This construction leads to exponential growth in the length of the strings, with the size of s underscore n being 2 to the power of n1. However, directly generating these strings for large n becomes computationally expensive and impractical. The key is to leverage this recursive structure to find the kth bit without explicitly constructing the full string. This insight is foundational to our approach. The recursive approach to find the kth bit begins by calculating the length of s underscore n1, which is 2 caret n1, 1. From here, we determine which part of s underscore n the kth bit belongs to. If k is less than or equal to the length of s underscore n1, the kth bit is in the left segment, which is simply s underscore n1. If k equals the length of s underscore n1 plus 1, the kth bit is the middle bit, which is always 1. If k is greater than this, the bit lies in the right segment, which corresponds to the inverted reverse of s underscore n1. To handle the right segment, we map k to its corresponding position in s underscore n1 and compute the inverted bit at that position. The base case occurs when n equals 1, where s underscore 1 is 0, and the only valid k is 1, giving a result of 0. With these rules in place, we can recursively trace the position of k back to smaller strings until we reach the base case and return the result. The problem's exponential growth in string length makes direct construction infeasible, especially for large n. Instead, we can exploit the recursive symmetry of the strings. A critical insight is that the right segment of s underscore n is derived from the inverted reverse of s underscore n1. This symmetry allows us to map positions in the right segment directly back to positions in s underscore n1, significantly simplifying the computation. Additionally, knowing that the middle bit of s underscore n is always 1 helps streamline the logic. No extra data structures are required beyond the indices we compute, making this approach highly memory efficient. In terms of complexity, the time requirement is O(n), since each recursive call reduces n by 1, and the space complexity is also O(n), due to the recursion stack. The pseudocode demonstrates this process, starting with the base case and checking whether k lies in the left segment, the middle bit, or the right segment. From the pseudocode, if the kth bit lies in the left segment, we recursively call the function on s underscore n1 with the same k value. If k equals the middle index, we directly return 1. If it lies in the right segment, we map k to the corresponding position in S_n1 using the formula nu_k equals 2 to the power of nk. After determining the position in S_n1, we compute the inverted value. Specifically, if the recursive result for the mapped position is 0, the final result is inverted to 1, and vice versa. We can see this logic applied in an example walkthrough, where we trace the position of k through decreasing values of n, using the recursive structure to narrow down the bit's location without constructing the full strings. In the example, we are tasked with finding the 11th bit in S_4. First, we calculate the length of S_3, which is 7. Since k equals 11 is greater than ES_3 plus 1, the bit lies in the right segment. Mapping k to S_3 gives nu_k equals 16, 11 is equal to 5. Repeating this process for S_3, we find that nu_k equals 5 lies in the right segment again, so we map it to S_2 with nu_k equals 8 minus 5 is equal to 3. Now, at S_2, nu_k equals 3 corresponds to the middle bit, which we know is always 1. As the recursion unwinds, the result is inverted where necessary, ultimately returning 0 as the final answer. This example highlights how we efficiently navigate the recursive structure to find the desired bit without explicitly building large strings. This Python solution efficiently solves the problem by leveraging the recursive definition of the binary string sequence without explicitly constructing the string, which would be computationally expensive for large inputs. The function findKTH_bit is the main entry point. It delegates the computation to the helper function find_kth_bit_recursive, which recursively determines the kth bit of S_n. ### key steps. 1. Base case: if n equals 1, the sequence S_1 is 0. Hence, the first bit is directly returned as 0. 2. Length calculation: for any n, the total length of S_n is 2*n1. This is calculated using the bitwise left shift operation, 1n, which is equivalent to 2*n. 3. Midpoint check: the midpoint of S_n is length //2 plus 1 based index. If k equals the midpoint, the kth bit is 1 since the middle bit in S_n is always 1 by definition. For recursive calls, if k is less than the midpoint, the kth bit lies in the first half of the sequence, which is identical to S_n1. Thus, the function recursively calls itself with n1 and k. 5. Mirrored position: if k is greater than the midpoint, the kth bit lies in the inverted and reversed part of S_n. To find the corresponding position in S_n1, the mirrored position is calculated as length k plus 1. The bit at this position in S_n1 is inverted to get the kth bit of S_n. By using recursion and avoiding explicit string construction, this approach ensures optimal performance even for the upper limits of the input constraints. The time complexity is O(n) due to the recursive calls, and the space complexity is O(n) due to the recursion stack. This is the Java implementation for LeetCode problem number 1545, find kth bit in nth binary string. The logic mirrors the provided Python implementation, using recursion to determine the kth bit in the nth sequence. Key differences include the use of Java-specific syntax such as primitive types and method declarations. The solution calculates the midpoint of the binary string and determines whether the kth bit lies in the first half, the midpoint, or the reversed and inverted second half. This approach efficiently handles the problem without constructing the full binary string. To solve the problem of finding the fifth bit in the third binary string, we start by understanding the recursive structure of the sequence. The first string, s, is 0. The second string, s2, is formed by taking s, appending 1, and then appending the reverse of s with the bits inverted, resulting in 0, 11. Similarly, s3, the third string, is constructed by applying the same process to s2, giving us 0, 1, 1, 1, 0, 0, 1. Now, we are tasked with locating the fifth bit of S3. First, we compute the total length of S3, which is 7, since the length of any S is given by 2, 1. The middle position in S3 is calculated as 4, and since k equals 5 is greater than this middle position, we know the fifth bit lies within the inverted and reversed part of S3. To determine its value, we map it to its mirrored position in the previous string, s2, using the formula length, k plus 1. This gives us a mirrored position of 3, so we now focus on finding the third bit in s2. In the second recursive call, we now need to find the third bit in s2. The length of s2 is calculated as 3, and the middle position is determined to be 2. Since k equals 3 is greater than the middle position, the third bit lies in the inverted and reversed part of s2. To locate its value, we compute the mirrored position in s using the formula length, k plus 1. This results in a mirrored position of 1. We then make a call to find the first bit in s. At this point, we have reached the base case since s is the simplest string, 0. The first bit of s is 0, so we return this value. However, because the bit is from the inverted part of s2, we invert it to get 1. Similarly, the bit from the mirrored position in s3 is also inverted, so the final result for the fifth bit in s3 is 0. Now, let's look at another example where we need to find the eighth bit of the fourth binary string, s4. The sequence builds as follows: s is 0, s2 is 011, s3 is 011, 1001, and s4 is 011100110110001. The length of s4 is calculated as 15, and the middle position is determined to be 8. Since k equals 8 is equal to the middle position, we can directly conclude that the eighth bit of s4 is 1. This is a key insight of the problem. The middle bit of any s is always 1, regardless of the value of n. Therefore, the final answer for this example is 1, and we don't need to make any further recursive calls. Finally, in our last example, we need to find the second bit of the second binary string, s2. The sequence is straightforward here: s is 0, and s2 is 011. The length of s2 is 3, and the middle position is calculated to be 2. Since k equals 2 is equal to the middle position, we know immediately that the second bit of s2 is 1. As with the previous example, this is because the middle bit of any s is always 1. Thus, the final answer for this example is 1. To analyze the time complexity of our solution, we start by considering the recursive depth. Since the function reduces the problem to the n1th binary string in each recursive call, the recursion depth is directly proportional to n, making it O(n). Now, let's look at the work done in each recursive call. Calculating the length of the binary string, the middle index, and performing conditional checks to determine the position of k all happen in constant time, O(1). Even computing the mirrored index, when required, is also a constant time operation. Since the depth of recursion is O(n), and each call involves O(1) work, the overall time complexity of the solution is O(n). Now we turn to the space complexity. The primary contributor here is the recursive stack. With the recursion depth being O(n), and each call requiring a constant amount of memory for parameters and local variables, the space used by the recursive stack is O(n). Additionally, the solution does not utilize any extra data structures or auxiliary memory outside of the recursive stack. All computations are done in constant space within each call. Therefore, the total space complexity of the solution is O(n). Let's compare this optimized recursive approach to a naive solution. In a naive approach, you would explicitly construct the nth binary string, s_n, which grows exponentially in size with n. The length of s_n is 2(n1), so constructing it would require O2 to the power of n time an O2 to the power of n space. Once the string is built, accessing the kth bit is O1. In contrast, the recursive approach avoids constructing the binary string entirely. Instead, it simulates the process of generating the string and directly retrieves the kth bit. This reduces the time complexity dramatically to O(n), and the space complexity to O(n). Importantly, the time and space complexity remain consistent across best, average, and worst cases since the recursion depth depends solely on n, making the recursive approach significantly more efficient for larger values of n. Finally, let's solidify our understanding with a mathematical justification for the big O complexities. The recursion reduces the size of the problem linearly with respect to n, and the work done in each call is constant. This gives a total time complexity of O(n). Meanwhile, the recursive stack grows linearly with the depth of recursion, which also scales with n, leading to O(n) space complexity. Compared to the naive solution, which suffers from exponential growth due to explicitly constructing S_n, this approach is vastly more efficient for large n. This efficiency stems from avoiding the memory and time costs associated with storing or generating the full binary string, making the recursive solution far superior for this problem. Let's start by addressing some common mistakes that can arise when solving this problem. One frequent issue is misunderstanding the recursive pattern used to construct the sequence. The formula S_i equals S_i1 plus 1 plus invert, reverse, S_i1 is critical. Both reversing the string and then inverting it are essential steps. Skipping either operation will lead to an incorrect sequence. Another mistake involves inefficient string concatenation. Using the plus operator repeatedly to build large strings leads to poor performance because each concatenation creates a new string, resulting in n² time complexity. Instead, you should use a list to accumulate parts of the string and join it at the end. Lastly, mismanaging the invert function can cause problems. The inversion logic must be precise. Every 0 should turn into a 1 and every 1 into a 0. Testing your invert function with simple cases, like invert 101, can help ensure it's working correctly. Another common pitfall is overcomputing the entire sequence. Generating the full binary string up to S_n, especially for large n, is unnecessary if you only need a specific position in the sequence. This approach consumes excessive memory and time, making it highly inefficient. A better solution is to use an optimized technique, like divide and conquer or binary search, to determine the value at the required index without constructing the entire sequence. Additionally, neglecting edge cases can lead to bugs. For example, scenarios like n equals 1 or queries at the very first or last index often behave differently and can expose flaws in your logic. To ensure your solution is robust, always include edge cases in your testing strategy. To perform well in interviews, there are several key insights to keep in mind. First, take the time to thoroughly understand the recursive formula. Walking through a few iterations manually will help you see how reversing and inverting interact to form the sequence. Next, focus on optimizing for index-based queries. Interviewers often want you to avoid brute force methods for large inputs, so strategies like divide and conquer are highly valued. It's also important to discuss the trade-offs of your approach. For instance, brute force has an exponential time and space complexity, while optimized approaches significantly reduce memory usage. Additionally, recognizing patterns, such as symmetry or palindromic structures, can simplify your solution. Finally, communicate your thought process clearly. When transitioning from a naive solution to an optimized one, explain your reasoning step by step. This problem also connects to several related problems that can help reinforce your understanding. For example, LeetCode 344, reverse string, and LeetCode 190, reverse bits, both involve reversing operations, which are integral to this problem. Additionally, LeetCode 476, number complement, focuses on flipping binary bits, which is similar to the inversion step here. Beyond these related problems, there are alternative approaches to solving the original problem. One such method is divide and conquer, where you determine whether the target index lies in the left half, the middle, or the inverted right half of the sequence. This approach minimizes memory usage and improves efficiency but requires careful bookkeeping to track positions. Another option is iterative simulation, where you simulate the process step by step, keeping only the current and previous states. While it's more memory efficient than brute force, it's still slower than divide and conquer for large inputs. A third alternative is to use mathematical analysis. By studying the sequence's properties, such as its symmetry or periodicity, you might be able to derive a mathematical formula to directly compute the result at any index. This is often the fastest approach, as it eliminates the need for recursion or simulation altogether. However, deriving such a formula isn't always feasible, as it depends on the complexity of the recursive pattern. When possible, this method can provide an elegant and efficient solution, but it requires a deep understanding of the problem structure. To wrap up, we've summarized the problem, discussed the key takeaways, and highlighted the insights gained from solving it. Thank you for watching. If you found this helpful, don't forget to like and subscribe for more tutorials. Keep practicing and happy coding. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!